Okay, good morning students. Welcome back to laser technology sessions. So in the last class we have discussed about the laser characteristics, right? So we have different laser characteristics like high monochromaticity, high directionality, high power or high intensity, and the coherence and ultra short pulses. So we are going by one. So we have discussed high monochromaticity, so that's also you can call narrow spectral width and high temporal coherence. So that's we have seen in the last class, and today's class we are going to discuss about remaining other properties such as directionality. So the directionality you can also call highly collimated beam or highly collimated laser beam. So these laser beams will give like highly collimated beam. So that means in your longer distances it can travel without losing much intensity. And also this you can call as diffraction limited collimation. So you might already know about what is diffraction limitation for the light, right? We can discuss in the little later. A small focus spot or diffraction limiting focus. So for example, now you have a light source, how tightly you can focus. So that is also you can have a diffraction limitation, so that how tiny you can focus it. Then we can compare with the conventional sources, whether the conventional sources can be focused tightly or your laser beams can focus tightly. So that we can discuss now. And also the directionality, it will also tell you the high spatial coherence. So in the monochromaticity it gives you high temporal coherence. High monochromaticity, that is nothing but high temporal coherence, so that at any later the time, so you can retrieve your amplitude or the phase information. Okay, but here with the high directionality you will also have same thing like high spatial coherence. Okay, for example, now if we take a conventional source, so in general the conventional source you works as a electric discharge phenomena. So you generate, this is our source height, that is our radiation generating. Okay, so then it will be a conical emission, then you use a lens to collimate the light. So you use a focal length f, then you able to collimate a beam. But how far this collimation, that depends upon the your source as well as how much light you are able to collimate. So there are the two things here. One is how good the collimation can be measured using the divergence angle. So the divergence angle will depend on two factors. So one is height of the source. Okay, for example, now your height of source is h, so if the h by 2 will you on the numerator side, that decides you whether divergence angle is low or high. For example, if h is increasing, your theta will increase. So that means if the source size is increasing, your divergence angle increases. And similarly, in the other way, your focal length increases. Your focal length increases, your divergence angle decreases. Okay, so if focal length decreases, your divergence angle increases. Now if you see, your theta is proportional to h, your height of the source, and theta is inversely proportional to your focal length. For example, now I will increase the focal length. What happens? Now I will shift the lens to this position. Now what happens? this is a divergent beam, this is a diverging beam. Okay, you will lose a lot of intensity, okay, if you use the same size of the your lens. Now if you use a bigger lens, now lens has a absorption properties or reflection properties. You cannot transmit all the 100% of the light. So if material length increases, the size increases, you always absorption increases, you will reduce the intensity passing through the lens. So in any case, if you increase the focal length, the amount of light will decreases to collimate. So that is one thing. And if you increase the height of your source, what happens? Your divergence angle increases. That doesn't work because you need a high intense beam. So now you have to decrease your height of the source, decrease your height of the source. Now how, if you decrease the height of source, the amount of light you generate decreases. So at any cost, it is almost impossible to give the high intense beam like lasers using a conventional sources. So these are the two reasons, because you will not get very high powers from your conventional source. It's completely source size dependent. Your light intensity or your collimation is clearly, it's a source size dependent, and you have a large light loss can happen using your conventional sources. You cannot collimate all the light. Now you take a laser beam, so your laser beam size of D, okay, so the laser is emitting a beam size of D. So now your theta is a divergence angle, so that is theta is almost is equals to lambda over D. So now your source size, we don't worry, because if you increase the D, still it's your theta almost whatever the divergence angle is decreased, but it cannot decrease than the your size of the beam. So that means you are always getting a nearly perfect collimation using your laser beam. Okay, for example, I will take a size of 2 mm of a beam. Now using optics, I can, using a beam expanders, I can make it 5 mm beam. So now even a 5 mm beam, I can have a clearly nearly a very good collimation can achieve. So that's why your size, source size, it's completely source size independent. Your collimation is a source size independent. It not really doesn't depend on the your source size, and your theta is almost close to your lambda by D. So this have certain factors, like some constant will come into the picture, that is very doesn't influenceable, but that is only for the, depending upon the different beams, it will change the constant factor. That is why your laser beam is like highly collimated. So in this case, your light loss will be very negligible for certain distances. Okay, so now what is the use of these directional beams, or you can say collimated beams? So it's very easy to align. So for example, if beam traveling in the longer paths with the conventional source, you will find very difficulties, because always the beam is diverging. It is highly difficult to align your experimental setups, or any experimental aspects of your alignments will be difficult in the conventional source. In the lasers, you can easily do it, the alignments, and these lasers will allow you to have a barcode readers and they will use these high direction beams in the communications and in the radar applications. So that is advantage of these highly directional beams. And now we will see the focal spot or a diffraction limiting focus. Now your conventional source, okay, you use a lens. So in principle this is collimation, you have to use one more lens to focus. Okay, I think there is a animation error, so you need one more lens to focus. So now when you focus it, you cannot get high intensity beam than your source. Okay, and similarly your focal spot source size dependent. Whatever the source size you take, you cannot focus more than that. For example, you have a 5 mm source or 10 mm source, you can focus up to 10 mm. So that is completely your focus is source dependent. So that is what the conventional source. In the ideal case, so I think you have a perfect light source, you assume that can be focused very tight. So how tight means you can focus whatever the wavelength you take, it can reach the wavelength of same size. For example, if you take 500 nanometer wavelength light, you can focus the focal spot to 500 nanometers. Okay, so that is the advantage of the ideal light source. So now if you see, you can ask me why you are not actually, in general in the ray optics you will see when a light propagating through a lens, you will have a spot like it crossing the two rays, right? But in general that is not the real picture. When you focus the light, so your light always comes to very close. Okay, this is your a wavefront. So you study a wave optics, then these are the plane waves, or you are trying to focus it, then this becomes the wavefront will be like this. After traveling a large distances, again they becomes plane waves, and also at the nearly focus they are also plane waves. So this you will study in the wave optics, how your light waves will propagate with the wavefront geometry. So you cannot focus to a point. Okay, so that is a diffraction limited. So that means you cannot focus your beam, your light shorter than your wavelength. So that is a diffraction limitation. So but with the ideal light source you can achieve almost close to your wavelength of light. So that is for the ideal light source. So now we can almost close to ideal source using our laser system. So now your laser delivers the light with the assuming your beam size of D. Now you can actually focus up to almost close to wavelength of the light. So that means you can focus to very tiny spots. Okay, so that is the more advantage of your laser beam. You take the wavelength, for example, if you take the wavelength of 100 nanometers, then you can focus up to 100 nanometers, provided the lens materials has to be having a good transmission and the focusability. Okay, so but in principle your laser doesn't have a problem. If you take the whatever the wavelength, you can focus up to the wavelength size. So that is the advantage of your laser system. This can act as a nearly ideal light source. So that is the great advantage we get from the lasers. The usage of these spot sizes, you can read a compact disc like CDs and DVDs. So there they use a laser focused spots, and in the laser printers, and to process the materials, like for example you want to like make a channels in the material, or you want to make a gratings, or you want to make any processing of your materials using a laser beam. Generally they will use a spot size. There at the spot size we will see the intensity always higher at the spot size, because all the light whatever you see, this is our diameter, like your diameter of the d of the beam. So you all the light with this diameter you are focusing to a tiny spot. All the photons you are actually focusing to a spot size of lambda or close to lambda. Now you assume all the photons at this same point, that means it's very bright and high intense. Okay, that is the way you can use different applications in for the medical surgeries, and this is will very beneficial. But in principle lens have a property. So because of the geometry, it can able to focus the beam. Okay, this is the optical axis. So whatever the light incident on the optical axis, that will not, the wavefront will not distorted, but in other case the wavefronts will be distorted. So now this is our wavefront, your planar wavefront. So at this point, because this is optical axis, this will not bend. You have like planar your plane wave remains same, but now this portion has to travel shorter length in the medium, and these portions will has to travel longer length. Okay, because of the longer length travel, it will bend. You can see the bending property how it happens. Okay, so that is the property of the lens. The spatial coherence, how the directionality will give a spatial coherence. So the spatial coherence means light wave is well behaved in space. Okay, so the same thing we studied with the temporal coherence, it will be well behaved in the time. So your amplitude and phase can be predicted at any spatial position at any given time. Okay, for example, now this is your source, these are your clean wave fronts. Okay, if you know an amplitude at one position, you can predict the, for example at this position you know the amplitude and the phase. At this position you can find out the phase as well as amplitude. To make it simpler, you use a lens so that you will get a plane waves. So now you know the amplitude and the phase here. At later time you can see here what is the amplitude and phase, you can get it. So that gives you your spatial coherence. Your coherence will allow you to predict the amplitude and the phase information at any spatial position. Okay, so now what about your conventional source? Your wavefronts are highly distorted. If you know the information of the phase and amplitude here, at later times even within the wavefront you cannot get it. Okay, so that is the difference with your conventional light sources and your laser beam. So your spontaneous emission emits at different times and also giving a different directions, that you don't have a phase information lock. Like the, see what is coherence means, that your phase information having a relationship between the wavefronts at later time scales. You always have a phase relationship, but in this case if you see at this point you take and later time scale at the same point, you don't have a phase correlation. When you don't have phase correlation, you cannot tell what is the amplitude or the phase information at the later time scales, right? So that is why you call this is incoherent. Okay, so now other laser characteristics giving a very high power. So we already discussed about CW lasers and pulsar lasers. Now CW lasers can give a milliwatt to megawatt powers. Okay, and your pulse lasers can give giga to hexawatt. Now you see how much power you are able to generate using laser systems. Even CW lasers you will get a megawatt, like 10 power 6 watts. If you ask me like what are the powers you get, the normal sources it's much very high less. It will be maybe if you get maximum in couple of lakh watts, not more than that. That is also the best conventional source can give. But lasers you can see many number of order of magnitudes. That is a huge difference. They can achieve a very high powers. Yeah, there is a typo here. So you can get a milliwatts to megawatt. So it covers 10 power minus 3 watt to 10 power 6 watt. So milli to mega. Mega means 10 power 6. At the pulse you will get giga to hexa. So you will get 10 power 9 gigawatt and 10 power 12 terawatt and 10 power 15 petawatt and hexawatt. Now the technology is getting the hexawatt powers. Okay, this is still we are continuing to extend the your power generation. So we don't know in the next couple of years or later how much power even we can extend, right? It's a continuous research is going on, but so far now the record values are in the hexawatt. Okay, so I will stop here. So I will continue in the next class.